This is lecture 2, part B. This is a continuation of discussion on memory. And so this was not super memory related, but it's going to be a preparation for the next lecture. And so it's working with tri-state devices. So the word of the day is shared resource, particularly a shared hardware resource. So it generally means if I can share something like a hardware resource, it's generally going to save money. It's going to save real estate, power consumption. Typically speaking, it's going to slow things down a little bit, but it's a trade-off between lower memory, less parts, and slowing your circuit down. It'd be nice to have as many things as you need to, but in a typical digital circuit, things are shared. And so that's what we're going to get into today. Essentially, tri-state is a mechanism to share devices in a circuit. So the two main things that are shared out there are hardware resources and routing resources. So we're not going to discuss hardware resources. We used to have that in the old architecture we used to use for this course. We're more interested in, for this discussion, routing resources. Okay, so one of the first things you need to do when you look at a new microcontroller is to look at the memory map. Okay, the memory map kind of tells you how the system is utilizing memory, for lack of a better word. Essentially, you're interested in what addresses do what to what parts. So in relation to memory, memory is not always like one thing. Typically speaking, it's like multiple memories that are put together in such a way that you can it looks like a big memory. You're modeling a big memory with a small memory. So typically speaking, memory in general, the slower memory is cheaper, and the lower power memory is slower. It takes a lot of power, takes extra power to have these circuits switch values, and if you don't need the speed, certainly you can save on power. So the thing we're moving towards, we're not going to quite make it here yet, but is in this course, part of the course is working with memory, so I want you to be able to piece together memories as you need them. So typically speaking, if you need a 128K by 8 RAM, you don't use a 120K by 8 RAM. You use a 264K by 8 RAMs, and you hook them up together such that the system thinks you have one memory. And so that's what we'll be going over here. And this is actually very useful because, quite frankly, you may need something like a 12K by 7 RAM, which is totally bizarre. Your system may need it. You're not going to find it off the shelf. You're going to need to make it or synthesize it yourself. Okay. So one of the things that's going to help you do this is the notion of tri-state devices. So tri-state devices means these, it's digital, so we have ones and zeros, but the implication is there's the third state, which we refer to as Z, which we consider a high impedance state. Okay, so high impedance state is something that I always toiled for years, but I was able to figure out how to model it in my brain in such a way that it actually works. So what we have is V equals IR, right? And I know people have worked with a resistance and impedance probably in your circuits courses. But if I switch this around, R equals V over I. Okay, so high impedance, the impedance is kind of like the resistance, for lack of a better word. We'll go with that. The issue here, if it's high impedance, that implies this is large. For a typical digital system, the voltage is fixed. It's not going to change. So if R is large, I is small. Okay, this works all the time. So that means high impedance means extremely low current. Extremely low current is close to no current. No current is close to an open circuit. No current is an open circuit. So the issue here is High impedance means that if I have a circuit element gone into high impedance, it means that circuit element is taking no current, which effectively means that circuit element is no longer in the circuit. It doesn't have the ability to drive lines, doesn't have the ability to do anything. So this is our vernacular here is this is a high impedance, or this is a buffer, a tri-state buffer. I have a switch on it. So here's the truth table for this thing. If this switch is turned on, this A signal is passed through to F, which you can see on these lines here. But if the switch is turned off, this output here, F, goes to high impedance, which essentially means this line here has no drive current, which effectively means it's an open circuit. So this having the ability to put something in a tri-state means I'm effectively like taking it out of the circuit, and that's how we're going to use it. And let's go forward here. Okay, so we have this is an example of a tri-state register. It's a normal register as you know and love it here, but it has this little triangle on the output which indicates the output is tri-stated. Okay, so once I have a tri-stated buffer or registered like this, I also have an enable input. The enable input puts this into either a non-high impedance state or a high impedance state. So when this is turned on, I have a normal output. When the enable is turned off, I have a high impedance output, and that's what I want to show you in this diagram here. So here's enable turns on and off. So once it turns off, I go into these high impedance states, and you can see that both times it turns off, it goes into a high impedance state. When it turns on, it just acts like a normal register, so you can see that this value right here, 32, gets loaded into there on the active clock edge because the load's turned on, etc., etc. Here we got no load, so it doesn't load. And well, other than that, it's just like a normal register. You can follow this through, see it load here. We'll do one more. So this is a clock edge. This is this combined with the clock edge makes that E7 load into the register. Fun stuff. We're not going to use that too much. We like the idea of knowing about it because we're going to use it in our memory problems. So this is an example of a high-level and low-level example of a tri-state register. Well, bidirectional. So we'll talk about bidirectional registers a little bit, for better or worse here. So this is a bidirectional register. It's tri-stated because I can see the triangle there. That means I can turn this thing on and off. So this register has the ability to drive data onto this line here, and it also has the ability to input data. And this is, I always was confused by this circuit, so I always try to remember it by this. Here's a normal register with a tri-state buffer in front of it. So if this register always has the ability to read data from the outside world, but if this register needs to drive its data into the outside world, I need to turn the enable on. Typically speaking, at no time, well, essentially when the enable is turned on, you're driving data into the outside world. You're never loading it. Typically you're never going to load the data from the register back into the register. It makes no sense. I mean, you could do that, but it's just not done. Typically speaking, when I'm accepting data from the outside world, it's going to come in through this line. I'm going to turn the tri-state off, come in through this line, get loaded in via the clock signal and the load signal. And that's all I can think of in that. Okay, so the point here is, once again, it's device sharing, and this is a circuit here. It goes, I know there's more in-depth examples in the book with two registers, but I mean, what can you do with two registers? If it was set up properly, that means I would need some muxes sitting in front of this thing. I could actually swap the data in these two registers in one clock cycle. But it's not set up that way. This is set up as a tri-stated circuit. You can see that these both registers have the ability to drive their data onto this single line here simultaneously, which they don't, of course. Two registers driving their data onto lines simultaneously is bad news. It's called bus contention. It's just not going to work. So essentially, only one of these registers at a time, or only one device per shared resource. The shared resource here is this line right here, or whatever it's connected to that too. The shared resource, only one device can drive its data onto that line at one given time, and I cannot swap data into these registers simultaneously the way it's set up. So because I have less hardware, I've lost functionality, but the trade-off is I have less hardware. So if this works for me, certainly it has less hardware, I'm going to use this. If this doesn't work, I'm going to drop some muxes in front of this thing and extra routing, and I'll be able to swap this data at the same time. Okay,